So,
I was going to
yes.
something else, but I'll just ask you. Do we submit all the files in the tar file or just the R?
So the question is, do you submit all the files in the tar file or just the .cpp? And you're only going to be submitting the .cpp files.
Okay.
Okay.
Not the executable or anything else?
Not the executable or anything else, because
All the dots.
just the .cpp. Just the ones right. You're not supposed to be modifying the .h file. Okay.
Right. Okay.
So if you're using, it's okay to add additional functions. We've actually had some students ask, is it okay to calculate the hash functions outside of the like insert and search functions, and that's fine. It's just you put them in the .cpp file. Okay. Okay, so we're going to be getting, whoops, not these notes. We're going to be getting started with pointers today. So we're going to be moving into a new concept, which in C++ we said there were two new concepts in this course. One was pointers, one was recursion. So today we start with one of the two new concepts in C++ that you'll be confronting this semester. And pointers are crucial to implementing the remaining data structures we'll talk about this semester, which are lists, queues, stacks, and trees. Okay, hash tables could be implemented using vectors, so that was a pre-existing data structure you knew about, but the remaining data structures we will use in this course are all what we call linked data structures, and they need this concept of pointers. Before I do that, I want to finish up talking about hashing. We didn't go over the performance of hashing, and that is crucial. Also need to go over a few things about the lab. So I'll actually go over the few things about the lab first. So in lab 4, there's some things I've noticed from previous semesters that want to make that are kind of gotchas. Okay, the first gotcha is what you see here, number 1. Make sure that your return values from the hash functions are stored in unsigned ints in your search and insert routines. So one problem is if you try to store the return values in integers, those are signed ints. And an unsigned int can come back with a 1 in the leading bit, which means if you try to assign it to a signed int, you will end up with a negative number and your code will segfault for the simple reason that you forgot that you were returning an unsigned int. So that's number 1. Number 2 is efficiency. So I cannot overemphasize efficiency, and unfortunately I feel like probably have not made it enough of an issue thus far. So anytime you perform unnecessary operations in a computer program, you are lengthening the time it takes for that computer program to run. Okay? In the exams, the exams will be back next Tuesday. We haven't quite gotten them graded yet, but we are working on them. So in the exams on the coding, I'm going through and I'm making comments. I'm generally not taking off points unless it's egregious, but when I see you making unnecessary operations that don't do any good, I'm pointing them out because that's an efficiency issue. And the reason we implement hash tables is because we want to make search more efficient. It's inefficient to do a linear search through a vector. Hash tables are a way to make searching and inserting much faster when using a vector. But it's really important that you don't throw away the efficiency by doing so-called dumb things. Okay? One of the things that you should avoid doing for double hashing is computing the second hash function when you don't need it. Okay? The whole point of hashing is that most of the time when you compute a bucket index, it's empty. And therefore you can insert the key without having to do any collision resolution. But what I see in a lot of programs is students, when they do implement double hashing, they go and immediately calculate both the H1 function and the H2 function. And then they never use the H2 function because the bucket's empty. That's an example of an inefficiency that you can avoid. Don't compute the second hash function until you're absolutely sure you need it. Okay? Because with hashing, we are very concerned about efficiency. That's why we were doing shifting instead of multiplying by 33. Efficiency is everything when you're computing those hash functions and doing searching and inserting. We'll do anything we can to shave a microsecond off the time. So don't compute that second hash function unless you need to. Another issue I've seen in the insert functions before is students will check to see if the table is full before trying to insert. That completely defeats the purpose of hashing. The only way to determine if a table is full is to search the entire table. Well, you just did a linear search. You just made it, there's no reason to do hashing after that. You just searched the entire table. So you threw away whatever performance advantage you were expecting to get with a hash table. Okay? So don't check to see if the table is full before trying to insert. The time to check is after when you failed. Now with linear probing, if you fail, you know you've checked the entire table. But with double hashing, you should check only after. If you fail with double hashing to insert into the table, only then should you check to see if the table is full. Okay? So these are small things, but they're huge as far as efficiency goes. And that's very important. We really are wanting you to focus on efficiency in your code. Okay? The final thing is something we didn't talk a lot, actually at all about. We may have a little, and the book has it, but when you're doing collision resolution, the question is, when should we stop searching for an empty bucket with insert, or when should we stop searching for the key with a delete or a find? Okay, we don't want to get into an infinite loop if there's no available bucket for insert or if the key is not there for search. Okay, so we certainly know that with search, we should stop if we find an empty bucket. But what could cause us never to stop on search? What? Yes. Okay. That's good, but that's not what I'm after here. So just open addressing in general, whether it's linear probing or quadratic probing or double hashing, any of these could fail by not, there's a reason why you might end up getting into an infinite loop. Yes?
If it just keeps like looking at the same few values, if you have like a table size 10, it just goes 0, 5, 0, 5, for example.
Right. So that's true for double hashing. Very good. But
Everything's full.
okay, everything is full. Right, good. So if the entire table is full, then you can't do it. Okay, it will keep going infinitely if you're not careful. Okay, because there is no empty bucket in the table. So that will fail for any of the three search techniques. So you have to know when to stop. It turns out that for linear probing and for double hashing, that you can stop after you have examined n buckets. Okay, so that's what I've said here. Linear probing, after n buckets, we've searched the entire table. Double hashing, after n buckets, we may or may not have searched every bucket in the table, but after n buckets, we will no longer look at a unique bucket anymore. That is, after the first n probes, we will no longer, starting at n plus 1, we're guaranteed we'll never see a unique bucket again. So you can stop in the lab if either you find an empty bucket or you have searched n buckets without success. Now, this isn't a math course, but it's useful to see that you can do proofs, okay, to show some of this stuff. So, for example, with linear probing, it should be pretty clear that after n buckets, we've searched the entire table because it's a brute force search. And it's just a linear search. So after n buckets, you've looked at every bucket. That's not clear with double hashing because with double hashing, I've told you that, and you've seen examples where the buckets can repeat. So someone could say, maybe after we get past to the n plus first bucket, it's possible we somehow don't repeat. Well, there's a proof for that can't happen. And it's a very simple algebraic proof. And it relies on a very simple algebraic thing that I won't prove to you. But in general, if you have a plus b mod n, that is equal to, you can separate it. You can say a mod n plus b mod n mod n. So that is a simple, you can prove it. I'm not going to, but that's the basis right there of our proof, that you can move the mod operator into the mod operation as long as you continue to mod the result. So with that simple thing, you can prove that double hashing will never look at a new value after the nth one. So if we say that the table size, I'm going to change table size here to n to make it clear. So this is G, 21, 24. I'm going to replace the table size with n. Okay, so I'm going to assume the table size is n. And what I'm saying is that after I've looked at n buckets, any bucket after that is not a new bucket. So what I'm saying is I'm looking at the n plus I bucket, okay, where I is now greater than or equal to n. So here, I is greater than or equal to n. Okay, so I can, using this axiom up here, I'm allowed to move the mod operator into the, first of all, I can separate it like I did here. So I have h of k plus I f of k plus n times f of k. So this is just multiplying it out mod n. And I'm skipping a step. I can write this as h of k mod n plus I times f of k mod n plus n times f of k mod n, all of this mod n. Okay, what is the value of this expression? Guaranteed. 0, because I'm multiplying by n. So this must be divisible by n. The dividend, or the quotient, is f of k, and there's no remainder. So this is a big fat 0. So what we end up with is plus 0 mod n, so I can get rid of the 0, and I'm back to this expression right here, but this isn't a unique bucket. I already looked at it, so n plus I gives me the same bucket as what I got with I. I'm sorry, I is not greater than or equal to 0. I is greater than or equal to 0. Not greater than or equal to n, greater than. So I get the same bucket. So when I'm at n plus I, the bucket I get is the same bucket that I would get for I. So I'm repeating. I can't get a unique bucket once I'm past n. Okay, so I can literally stop after I've done n probes. Okay. Now, you might wonder about quadratic probing. Okay, and generally we talk about quadratic probing with a prime table size, prime number for a table size. It turns out that for quadratic probing, you can stop, whoops, this is wrong place in the notes. So for quadratic probing, you can stop after the ceiling function of n divided by 2, where n is the table size. So after you get through with n divided by 2 table ceiling, so for example, e.g. with n equals 13, you can stop after 7. And again, you can do a fairly simple algebraic manipulation to prove that fact. Okay? So in this case, if we have quadratic probing, let's say that we have some I that is between, let's see, 0 is less than or equal to I is less than or equal to n divided by 2. And we want n, we want to look at everything then with n minus I is going to be, in this case, n minus I is greater than n divided by 2, but is less than or equal to n. Okay? So what we're caring about is everything between n divided by 2 and n, because that's what I'm claiming. I'm claiming every one of those duplicates a bucket I've already seen. Okay, so let's take a look at that. My claim is that, so let's do it. With quadratic probing, it is h of k plus n minus I times n minus I, because that's what quadratic probing is, mod n, which is the table size. Okay, well, if we write that out, that's n squared minus 2 times n plus I times I, mod n. All I've done there is a simple multiplication of n minus I times n minus I. Correct? All I've done is multiply it out. What is n squared mod n? 0, because n squared divided by n is equal to n with a 0 remainder. So this is h of k plus 0. Okay, what is minus 2n mod n? And what's the quotient? 2. Okay, so 2n mod n is 0 plus I times I, mod n, which is equal to h of k plus I times I, mod n. Well, we already looked at I, because we said that I was between 0 and n divided by 2. So we just proved through a simple algebraic proof that the bucket we look at in quadratic probing in a prime number for, actually it's not even prime. It can be any table size. It doesn't matter. This holds for any value of n. What we've proven is the bucket we look at for n minus I is the same as the bucket we would look at for I. Okay? And I'm not going to go through the proof for I greater than or equal to n, but you'll find with a similar, very simple algebraic manipulation that bucket n plus I is going to map to the same bucket as I, doing the same algebraic. So that's why you can stop after you've gotten to ceiling of n divided by 2, because you'll never see another unique bucket again. So questions about that? These were all related to, just circling back, this was all related to when we can stop after we've done some number of probes with collision resolution. With the lab 4, with linear probing and double hashing, we can stop after n probes. If we were implementing quadratic probing, which you are not, you could have stopped after the ceiling of n divided by 2 probes. So questions about that? Okay. So then just looking at the very bottom, whoops, of the hashing page, I wanted to go over the performance comparison for the 4 different algorithms we considered, which was separate chaining, and then the 3 open addressing schemes that handled, that was linear probing, quadratic probing, and double hashing. So these are the expected number of probes for each of the schemes given a successful, or given a insertion, a successful search, and an unsuccessful search. And you'll see that there's nothing here for delete. The reason there's not, can anyone say why I didn't bother with delete? Delete is covered in this table. It's a search. So whatever it costs for a successful search is the same cost for a successful delete. Whatever is the cost for an unsuccessful search is the cost for an unsuccessful delete, because delete first has to find the key. So L here stands for the load factor. Remember, the load factor is the measure of the fullness of the table. It's the number of keys. So if you remember the load, this is Firefox, great. Let's switch over to Chrome. Because in Chrome, I can use my tablet. So the load is equal to the number of keys divided by the table size. So it's how full the table is. So you can see for separate chaining, if we choose for separate chaining, we try to choose the table size to be equal to the number of keys to be inserted. If we manage that, then insertion on average just takes 1 probe, because we expect that there is at most 1 entry per bucket. Successful search, you may have to look at 1 entry. So it's L divided by 2, because sometimes there'll be an entry there, sometimes there won't. So it's effectively L divided by 2. For an unsuccessful search, and you could find it. It could be the 1, whereas for unsuccessful search, it might not be the 1, so you may have to go past it. So I'm just hand waving it, but these are roughly the ones for separate chaining. So with the load factor being 1, which it usually is for separate chaining, we on average never have more than 2 probes for any operation, which is excellent. It's constant time. Okay, we only look at 2 entries in the entire vector. With linear search, we might have to look at n entries. Okay, it gets more complicated with these other open addressing schemes, and there's rather complicated math behind it. But the important thing to look at is the 1 minus, is this divisor right here. 1 minus L squared in the case of linear hashing, but only 1 minus L in the case of quadratic probing and double hashing. That's huge. Okay, so if you look at things like a load factor of 0.5, then when you have 1/2 of 1 plus 1 divided by 1 minus 0.5 squared, that's equal to 1/2 times 1 plus 1 over 0.25, which is 1/2 of 1 plus 4. That's not bad, right? That's only 2.5 for an insert. So with a load factor of 0.5, it's pretty good. What about a load factor of 0.9? Okay, with a load factor of 0.9, it's going to be 1/2 of 1 plus 1 divided by 0.1 squared, which is 0.01. So we're going to end up with 1/2 times 1 plus 1 divided by 0.01, which is 100. Now we're up to 51 divided by 2. That's horrible. At 0.9, we're all the way up to, on average, looking at 25.5. That's no longer looking so much like constant time. That's getting big. And in general, that blows up pretty fast. If you look at the curve for the load factor, with this being the load factor going from 0 to 1, and this being the number of expected probes, it's going to, and this is 0.05, it kind of hits an inflection point around 0.05. It's going up, and then it starts to explode, which isn't good. That's why we generally choose 0.05 as our load factor for open addressing, because beyond that, the expected number of probes starts to increase very quickly, in fact, exponentially. And you can see successful search isn't quite as bad. It's 1 minus L. But unsuccessful search is also 1 minus L squared. Okay, so not so good. Now if we look at quadratic probing and linear double hashing, the first thing you should notice is that it's essentially the same things. 1 divided by 1 minus L plus 1/2, 1 divided by 1 minus L. 1 divided by 1 minus L plus 1/2, 1 divided by 1 minus L. And I'm going to have to go back and check this successful search because I think that it is also, there's a 1 divided by L in front of the double hashing. So I will check that. I think quadratic probing and double hashing also have the same factor, with quadratic probing being 1/2 a probe more. Basically, quadratic probing on average for each of its operations requires about 1/2 a probe more than double hashing, which isn't bad. So double hashing is better than quadratic probing, but only by about 1/2 a probe. And if you look again at the difference between a load of 0.5, back in Firefox, so if you go back here, we'll do a clear, come back here, and you look at these numbers again. So we're going to look at a load of 0.5, and a load of 0.9. Okay, for 0.5, 1 divided by, effectively, 1 minus L is 0.5, so it's 0.5 plus a half. We're looking at 2.5. And for 0.9, we're looking at 1 divided by 0.1 plus a half, which is essentially 10.5. Better than 50.5, or 25.5 rather. Still not great, but it's not going up quite as quickly. Still not wonderful, and much bigger than separate chaining. Okay, so here's the bottom line. We tend to use separate chaining in practice because it tends to have the best performance on average. However, separate chaining does take up a bit more storage because you have to, in effect, have a vector for every bucket. And that vector effectively exists and takes up memory. So separate chaining typically requires more memory than open addressing. So when embedded processors like sensors or your mobile phones came into being, there was renewed interest in these open addressing schemes because they use much less memory. And in embedded processors, there's limited memory. So you may, in an embedded processor, see them using a version of open addressing. Usually it will be quadratic probing. And the reason it will be quadratic probing is because it is much more efficient than linear probing and less computationally expensive than double hashing. Remember Goldilocks? Quadratic probing is the Goldilocks of open addressing. Double hashing, because you have to do a second hash function, the computation of that second hash function wipes out the extra half probe that we would use with quadratic probing. That is, the extra computational effort associated with computing that second hash function is far more than the cost of an extra half probe. So we use quadratic probing generally in practice. What technique did you not use in Lab 4, of course? Quadratic probing. The reason is linear probing is easier to implement, and double probing or double hashing gives you a better idea of kind of the extra things you can do with open addressing. So that's why you did linear probing and double hashing. In the remaining labs, you'll be using separate chaining because it's the most efficient technique. Okay, and again, it's important to choose a prime number as the table size. In fact, if you have a prime number as a table size, remember you can guarantee that half the first n divided by 2 entries you look at with quadratic probing will be, why is this? There we go. With quadratic probing, if the hash table size is prime and the load factor is less than 1/2, we're guaranteed we will always find an empty entry. That's another reason to keep the load size less than 1/2. It also turns out that with double hashing, if we choose the table size to be prime, that the double hashing will look at all n buckets, but only if the hash function is prime. And again, you can prove that through some simple algebraic arguments. Now in Lab 4, the reason why double hashing may fail is Dr. Planck doesn't guarantee that the table size is prime in the test cases. But if the table size was guaranteed to be prime, then you would know if double hashing failed that the hash table was full, because if the table size is prime, double hashing is guaranteed to look at every single bucket with the first n probes. Okay? So that is pretty much it. It's our first data structure that we looked at. It turns out that it's probably the most widely used data structure. For example, all scripting languages use hash tables as their workhorse data structure. Now, you may have heard a scripting language called them dictionaries or associative arrays. But if you hear the word dictionary or associative array, what they're really saying is hash table. So hash tables are really the workhorse of the computer science world. And the reason is they effectively give us constant time insert, find, and delete. And that's the other, you can't do better than constant time. Okay, so hash tables really are kind of the holy grail. They give us constant time, expected constant time for insert, find, and delete. Now, if the hash function is horrible and everything hashes to the same bucket, it becomes worse. Now it's order n because everything is hashed to the same bucket and it's linear search. So if your hash function is really horrid, for example, if I choose my hash function to be h of k equals 3, everything will hash to bucket 3, and I'll be reduced to linear search. So everything in hash tables is predicated on the hash function producing a well-distributed random key. And the DJB hash that we went over is a good one for that. It is just about as good as a random algorithm, a random number generator. Okay, the ACM hash I'm not going to hold you responsible for. It's very complicated and it doesn't do any better than DJB hash. But DJB hash works great. It's fast, it randomizes beautifully. It really doesn't matter whether it uses bitwise exclusive or whether it uses a plus. I think the only reason the author went from plus to bitwise exclusive or is bitwise exclusive or is faster. Okay, it goes through the Boolean circuitry in the hardware rather than the integer arithmetic, and that's the doing bit operations is faster than doing integer arithmetic. That's the only thing. But speed is everything when it comes to these insert, find, and delete algorithms. Okay? You would not be happy if Google took a minute on every search. So speed is everything. Questions about hashing before we move on? Okay. So, as I said, we're starting now into our remaining data structures we talk about this semester will involve some kind of linking between the different elements. And to do that linking, we have to introduce you to a new concept called pointers. So I'm going to, first of all, give you a couple motivating examples. Actually, let's look at what a pointer is. Let's give you a couple motivating examples first. Okay, then we will. So my first example is, let's say we're implementing our personnel at UT. And we have three different kinds of personnel: administrators, which I'll say ADM, professors, actually we have more, staff, and students. And sometimes a person can be more than one of these roles. A professor could actually be an administrator, a professor, and even a student at times. A staff member might be a staff member and a student. Okay? A student could be a student, well, same thing, student and a staff member. So let's say we have a record that's 100 bytes. And it's got information like the name and maybe an address, maybe an email, some other information. And I'm storing people on the list that they belong to. Well, let's say that there's a professor, there's a professor that is an administrator, a professor, and a student. If I am trying to model this professor right now, I need to store that professor on 3 different lists and duplicate their record 3 different times. So that's 100 bytes on each list. Plus, if I change the information about the professor, such as their email address, I have to remember to change it on 3 different lists. That's pretty hard to remember. I may have to search every single list. What if instead I were able to point to the record? So instead of having to have a separate record on each list, what if I could instead, on these lists, have, whoops, boy, that's not what I wanted. Still not what I wanted. Uh-oh. Cut. There we go. Uh-oh, it's still. Golly. Okay, back here. Hopefully it fixed it. Okay, yes. So there's a little thing on this pen. If I push this thing right here, it thinks that I want to go into drawing mode. So I have to be careful. So what I want now is just something in each of these points off to a same record. So now if I want to change the record, all I need is to change the record in one place. But the problem is, how do I, quote, have these pointers? How can I point to a record? So that was the problem that was considered by the developers of the C language back in the early 1980s. And they pondered, and you need to know something else about the solution they came up with. So in memory, every variable is stored at a memory address. So when you store something, memory goes essentially from 0 way up to some very large number, which we represent with hex digits. So we represent memory addresses with hexadecimal digits. Okay, they get up to very big numbers. And we have 4, 8. Normally, we think about memory in 4-byte chunks because integers are 4 bytes. Doubles are supposed to be 8 bytes. But everything, if you remember from 130, tends to be aligned on boundaries divisible by 4 if possible. Although doubles have to be aligned on boundaries divisible by 8. But at any rate, the point is every variable is assigned a memory address. Okay? Which means that this record up here has a memory address. So the people who pondered, let's say that this memory address is 0x100. So the people who developed C said, okay, we know that this record is at memory address 0x100. So what if we could somehow just say in here that the record we're interested in is at memory address 0x100? How do we do that? And they hit on the notion of a pointer variable. So a pointer variable is a variable declared like this. This says that IP is a pointer variable that can point to an integer. So IP okay, so IP is a pointer variable. That points to an integer. to an integer variable. Okay? So what it is its value, so that's 1, this is 2, its value is the memory address. Of a variable. So rather than storing an integer, it stores the memory address. Whoops, I don't want memory of a. So a pointer variable, its value is the memory address of a variable. So it's pointing to another variable. So that's what I get back here is I'm going to use pointer variables to point to this object. And each of those pointer variables would have the same memory address, which is the memory address of this object. So the developers of C, and later C++ is the follow-on to C, said, okay, the way we declare a pointer variable is putting an asterisk. See this asterisk in front of the variable? That says it's a pointer variable. Okay? So here are some very simple operations on a pointer variable. We start with an integer I and an integer pointer, which we call IP1. And the way you get the memory address of a variable is with the ampersand operator. So the ampersand operator is going to return the memory address of that variable. Okay, so the ampersand, darn it. So ampersand returns the memory address. Of a variable. Okay? So what we've done now is stored the memory address of I into IP1. Now we assign 5 to I, and when we print out I, we will get 5. Okay, now look at this statement. We have star IP1. Actually, up here, let's look at this. We print out star IP1 up here. When we put a star in front of a pointer variable, we want to go to the memory address pointed to by that variable and get its value. So what we're saying with this asterisk right here is we're saying return the value of the variable at the memory address stored in IP1. So in this case, the variable whose memory address is stored in IP1 is I. So when we print out star IP1, we're really printing out the value of I, which is 5. So when we do this printf statement, it's going to print 5 as the value of star IP1. Now we see star IP1 on the left side. Before, it was IP1 by itself. Now we see star IP1. What we're telling C++ in this case is that we want to store 10 not in IP1, but in the variable to which IP1 points. So this statement right here stores 10 in the variable to which IP1 points. Get used to me saying this. It's too hard and awkward to keep saying that I'm going to store 10 at the memory address that is stored at IP1. The reason we call them pointer variables is because they have a very natural meaning. They point to another variable. So when I leave the star off in the assignment, I'm making that pointer variable point to a new variable. I'm giving it a new memory address. When I put a star in front of that variable, I am now saying, if it's on the left-hand side, that I want to assign the value to the variable to which that pointer points. So here, up here, I was saying assign a new memory address to IP1. Make it point to a new variable. Here, I'm saying assign 10 to the variable to which IP1 points. The reason for the star is it disambiguates for the C compiler what I want to assign to. Right? Because there's two different memory addresses I could be assigning to. So the star disambiguates it. So now when I set star IP1 to 10, the value of I is going to change as well. In fact, that is what changes. I changes. And then when I set I to 15, that again changes the value of I, and if I print out star IP1, it will also print out 15. Okay? Make sense? Any questions? Okay. So, let's do something else for a moment. Going to actually code this up. Not code it up. I'm going to copy and paste it. Not that one. This one. There we go. Going to insert it into there. Now, what I'm going to do is something a little bit different. I am also going to print the memory addresses so that you can see what's going on. So I'm going to also include here IO string because it's a little easier. So I'm going to say cout address of I equals, and I'm going to print the address of I. And now, after I assign the address of I to IP1, I'm going to print out value of IP1 equals IP1. And then I'm going to print out value of variable to which IP1 points equals star IP1 to show you that you get two different values here. So first I'm printing out the address of I. Then I assign the address of I to IP1, so I'm proving to you by printing out the value of IP1 that it now has the memory address of I. And then I'm proving to you that by printing out the value of I, it is IP1. So in fact, I'm going to say I equals 3 here before I do anything so that I've assigned a value to it. We good with that? Okay, so now, actually let me leave that up. Get a new window. Make that smaller. Compile that file. And run it. C++ requires a type requires a type specifier. Dr. Planck's got somewhat. Main needs an int. Okay, compile it. Run pointer 1. And I have to now make this just a little bigger. So you can see address of I equals some really big hexadecimal number. So pointers are always printed as hexadecimal numbers because it's just, if you printed it in base 10, it would be even huger. The other reason we think about pointers as hexadecimal numbers is pointers are really 32 or 64-bit quantities. Okay, in this case, it's a 64-bit quantity. So there are 4 bits for each hexadecimal number because 4 bits is equal to 16. You can represent 16 with 4 bits. So you divide the 64 bits into 16 chunks of 4 and you get 16 hexadecimal numbers. Very nice. So people who think about hardware, and those of you who are in here who are CPE majors have to think about hardware a lot. You think about hardware addresses in terms of either 32 bits or 64 bits, and we divide those bits into packets of 4, groups of 4. Each group of 4 gives you a hexadecimal digit. Is that clear? Because you're going to have to think in terms of hexadecimal for pointers. Okay, so the address of I, this thing, sure enough, when we assigned it, IP1, when we assigned it the memory address of I, it got this big hexadecimal number. And then the value of the variable to which IP1 points is 3. So when I printed out star IP3, I got 3. So that's the essence of a pointer variable. Okay? It contains the memory address of another variable. Okay, so this by itself isn't, okay, and here Dr. Planck is just using pictures to show what is going on. I did it a little bit differently, but he's breaking down his code. So conceptually, when we define I and IP, we have 2 variables. When we set IP to be the memory address of I, we effectively make IP point to I. We assign 5 to I. Then when we assign 10 to star IP, we're assigning 10 to the variable that IP points to. IP points to 10, I'm sorry, to I, so 10 gets stored in I. So he's using pictures to show you what I just described. Okay. Now, there's a second thing. By itself, just pointing to, now, let me tell you something. Reference parameters. Remember reference parameters? Now I can tell you how reference parameters are implemented. Reference parameters are implemented by passing the memory address of the argument to the parameter. So when I say, for example, when I'm in a main, and let's say I have int I, and I has a memory address of 0x100, and now I call foo of I, and in foo, what I have is a reference parameter, say int reference j. J now actually has the value 0x100. So reference parameters store the memory address of their argument. That's what a reference parameter is. It's storing the memory address of its argument. And when you change a reference parameter, it's actually changing the value at the memory address. Yes, Thomas? So people who programmed in C and later programmed in C++ were disgusted, actually, when they introduced reference parameters. That's why Dr. Planck talks about taking the red pill. He thinks reference parameters are disgusting because they're essentially pointer variables, and he feels that the developers of C++ managed to confuse everything by introducing what is essentially a pointer variable and calling it a reference variable instead. The C++ developers said that pointer variables look nasty, and once we get further into pointer variables, I can show you swap, implement it using reference variables, and implement it using pointer variables, and it looks prettier with reference variables. So basically, reference variables were meant to hide some of the syntactic ugliness of pointers. But for people who are just learning the language, it is incredibly confusing, even for experienced programmers, which just causes people to ridicule reference variables endlessly. Okay, so most professional programmers hate reference variables. And in Java, they're done away with because they're considered to be confusing. So the answer to your question is well, we know why they did it. Most professional C++ programmers do not accept it as a valid reason. They think it made matters worse rather than better. It was introduced for readability's sake, yes. And that is not considered to be a good reason because it's how confusing it is. Okay, so moving back, not there, here. By themselves, pointer variables don't give you a lot. For example, back here, I want to point to this object, okay? Well, it turns out that if all you can do is point to stack variables, it's not very helpful because stack variables have this nasty habit of disappearing as soon as a function returns. Okay? With vectors, we're able to store more than one instance of an item, right? So with a vector, we can say vector people or person, and it would store some number of person objects. So what we want to be able to do is point to person objects, but when we don't want those person objects to go away when the function returns. Like this vector goes away when the function returns. That's no good. So we need to have a notion of long-lived memory, memory that can persist for the entire length of a program, not just for the lifetime of a function. There's a difference between the lifetime of a function and the lifetime of a program. Think of a web browser. You may have a web browser up for days at a time, yet the functions that a web browser calls often exist for only a couple milliseconds at most. So we have to have a way of having objects persist for the lifetime of a program. And we can't do that on the stack because stack allocated variables disappear as soon as the function returns. The solution for that is something called heap allocated variables. In fact, I'm going to go back for a moment here. And we have something called heap allocated variables. So it turns out there is 2 places you can store variables in a program. Up to now, you could only store variables on the stack using functions. So they are called stack allocated variables because they exist on the stack. So when you have a program, you have a place for its code, you have a place for its globals, you have a place for its stack, which often is growing up, and you have a place for what is called the heap. The stack grows up, the heap grows down. The heap is a heap of memory, a mound of memory, a heap of memory, hence the word heap. And it is where we can allocate variables that we want to persist indefinitely, for as long as we care to have them exist. Whereas on the stack, that's where you get the variables for functions, and those variables have a limited lifetime. So for on the stack, it is lifetime limited to the function. To the lifetime of the function. Okay, as soon as the function returns, the variable ceases to exist. Okay, here the lifetime is indefinite. They can last as long as you want. So how do we allocate a variable on the heap? Okay, the way we do that is with the new operator, right there, new int. This allocates a new unnamed variable with enough memory to store an integer. And new returns the memory address of that variable. So new is going to do 3 things. Okay. So it, right here, what new does? New allocates sufficient memory to hold an object of that type. So it's always new. You always are saying something like x equals new and some type, where type can be either a primitive type like an int, a char, or it can be a class like a string or a vector or a person. So it allocates sufficient memory to hold an object of that type. The next thing it does is calls the object's constructor if needed. What that means is if it's not a primitive type, if it is a class type, it then calls the object's constructor to initialize the memory. And then it returns a pointer to the object's memory. So 3 things. Allocate a piece of memory big enough to hold a value of that type. Call the constructor for that type to initialize the memory. Return a pointer to the object's memory. Okay, so just like you can make a pointer variable point to a stack allocated variable, you can make a pointer variable point to a variable allocated off the heap. And that is the real value of pointers, being able to refer to these long-lived pieces of memory. And you can assign to those heap allocated variables in the same way that you did to a stack allocated variable using a pointer. You say star and the pointer's name, and it now stores this value still at the memory address to which this pointer points. So in this case, 10 gets assigned to the memory that occupied by that new integer. Okay, so he has a quick example, and I'll let you go. But let's just look at his example. He has int I and int star. He has two integer pointers, IP1 and IP2. His first action is to make the first integer pointer, which he has a bug. This should be IP1. He's making it point to I. And then he's assigning I equals 5. Next, he makes IP1 point to this heap allocated integer. You'll see it's unnamed. Okay, I'm just going to hold you for a couple minutes. It points to an unnamed integer. And now he assigns 10 right here to that. Right there, he assigns 10 to that unnamed integer. Then he calls new again, which creates yet another integer, and he assigns 15 to it. You'll notice that this original heap allocated integer no longer has a pointer to it. We call it a memory leak, and we'll get to that next time, next Tuesday, because nothing points to it, which means it's lost. Okay? Now we make IP2 equals IP1, so IP2 points also to that unnamed integer. And when we assign 20 to IP2, it now has 20. And the final thing we do is we create a new integer, assigning it the memory address of IP1. We assign 25 to it, and now IP1 points to the new integer. IP2 continues to point to the old integer. So go over these notes between now and next time. Next time we'll start out with a little exercise to see how well you understand pointers, and then we'll go further into them.